So today we're looking at periodic trends, and when we talk about periodic trends, okay, we're looking at trends in atomic properties, all right, and ionic properties down the group and across the period. Okay, specifically, we'll be looking at atomic radius, ionic radius, and ionization energy. Okay, so the first trend that we're going to look at is the trend in atomic radius. Okay, trends in atomic radius. All right. Now, let's say, for example, we're looking at group 1 elements. Okay. Let's say we're looking at group 1 elements, right, in the periodic table. And we have lithium, we have sodium, we have potassium, and so on, right? So we're just looking at the first 3 elements for now, but this trend will apply to all the elements, right? The question is, what happens to the atomic radius as you go down the group? So we can say that atomic radius increases down the group, right? Atomic radius increases down the group. So the reason why the atomic radius increases down the group, right? Here's a diagram that shows the electronic configurations of lithium, sodium, and potassium. And what we can see is that down the group, the number of shells increases, right? And the number of shells increases, right? Because lithium has 2 shells, sodium has 3 shells, and then potassium has 4 shells, right? The outer electron gets further away from the nucleus, right? The outer electron gets further away from the nucleus. So obviously the radius is increasing, right? And secondly, because the number of shells is increasing, what that means is, remember, outer electrons are repelled by all the inner electrons, right? So in lithium, the outer electron is repelled by these 2 inner electrons that's sort of trying to push the electron further away from the nucleus. Whereas in sodium, this outer electron is repelled by the second shell as well as the first shell, right? So this outer electron experiences greater repulsion or greater shielding due to inner electron, whereas in potassium, that's the greatest, right? You have way more electrons in inner shells. You have way more electrons in inner shells, which means you have greater shielding or repulsion due to those inner electrons. Okay. So then what we can say here is that atomic radius increases down the group. Okay. The reason why is because the number of shells increases, right? The number of shells increases, hence the outer electrons are further away from the nucleus, further away from the nucleus. Okay. and experience greater shielding or repulsion due to inner electrons. Okay. And experience greater shielding. Again, shielding is repulsion due to inner electrons. Okay. So because they're further away from the nucleus and they experience greater shielding, okay, we can say therefore they are not as closely attracted to the nucleus. Not as closely attracted to the nucleus. So again, this trend, okay, this trend in atomic radii, okay, applies to all the groups. All right, so we'd see the same trend. We'd see the same trend in group 17. We'd see the same trend in group 2, and so on. Okay, so what we can say is that the atomic radius. Okay, we talk about the atomic radius here. For example, if we talk about group 1, right, we know that potassium would be greater than sodium. That would be greater than lithium. Right, if we talk about group 17, for example, right, iodine would be greater than bromine, which would be greater than chlorine. So now let's look at trend in atomic radius across the period. Okay, trend in atomic radius, right? And now we're going to look at the trend across the period. So for example, let's say that I have period 3 here. Okay. Let's say I have period 3. and period 3 I have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. So when we talk about the atomic radius across the period, right, we can say that across the period the atomic radius decreases. Okay, the atomic radius decreases across the period. Right. Now to understand this trend, right, here I have a sodium atom. Okay, a sodium atom has 3 shells, right? It has 3 shells like this. Very poorly drawn sodium atom, right? It has 3 shells, and the configuration, right, is obviously 1s2, 2s2, 2p6, 3s1, but here I'm just showing you the dot and cross diagram, right? So we have 11 electrons in sodium, and then if you look at a chlorine atom, for example, right? If you look at a chlorine atom, we have 17 electrons, right? So we have the same number of shells. So here I have a sodium atom, and here I have a chlorine atom, right? Now the charge in the nucleus for a sodium atom is 11 plus, right? There's 11 protons in the nucleus of a sodium atom, where there are 17 protons in the nucleus of a chlorine atom, right? Now if you look at the outer electrons, in both atoms, right, we just have 3 shells. So the outer electron is not further away in either of these two, right? And secondly, we have the same number of inner electrons. So the outer electrons in sodium are being shielded by the electrons in the first shell and the second shell, right? They're experiencing repulsion from these inner electrons. And you have a similar degree of shielding in a chlorine atom as well, right? The inner 2 shells are repelling the outer electrons. What that means is that the outer electrons in sodium and chlorine, right, are in the same shell, and they're experiencing similar degrees of shielding or repulsion due to inner electrons. However, chlorine has a much bigger nuclear charge, right? So the outer electron is not more shielded, but it is attracted much more strongly because of the increase in nuclear charge. And this explains why atomic radius decreases across the period. Because that outer electron is attracted more strongly, it will be held closer to the nucleus. Okay, so what we can say here is that across the period the atomic radius decreases, right? And the reason why is that the nuclear charge increases across the period, right? Increases across the period, whereas the number of shells, and therefore shielding remains the same. Hence we can say that the outer electrons experience greater nuclear attraction, right? Experience greater attraction from the nucleus, or greater nuclear attraction, and are held closer to the nucleus. Over here, of course, when we say the nuclear charge increases, right, the reason why is because the number of protons in the nucleus is increasing, right? So that means that the nucleus is increasingly positively charged, right? The positive charge in the nucleus increases across the period. You also have an increasing nuclear charge down the group, right? We know that potassium would have a greater nuclear charge than sodium, right? And sodium would have a greater nuclear charge than lithium. But in this case, the increasing number of shells and the increase in distance and shielding outweigh the increase in nuclear charge. Okay, this outweighs the increase in nuclear charge. So I'll write that down. Okay, the increase in the number of shells and the increase in shielding, okay, outweighs the increase in nuclear charge. Outweighs the increase in nuclear charge. So this is the idea when we talk about the atomic radius across the period and down the group. Okay. So if we had to show this graphically, all right, it's not an exact linear graph, but if you are asked to sketch it, you can just draw a line. Okay. You can just draw a line. So if we, for example, we were looking at atomic number, right, and radius, right, atomic radius, right. If we have, let's just say we're looking at period 3. We're just looking at period 3, right? That is sodium, magnesium, aluminum, silicon, phosphorus, which is 15, sulfur, which is 16, and then chlorine, which is 17, right? If you look at the trend in atomic radius, right, this is what the trend would look like. It's just a generally decreasing trend. Okay, so you can just draw a decreasing line like this. It's not exactly a straight line. There is variation, but if you're asked to sketch it, you can just draw a straight line. So here we have a table that summarizes these trends, right? If you go down the group, for example, from lithium to sodium, or from beryllium to magnesium, right, or from boron to aluminum, right, what we see as we go down the group, the atomic radius is increasing because the number of shells is increasing, right, which means that the outer electrons are further away from the nucleus and experience greater repulsion due to more inner electrons being present, right? So that's greater shielding, which means that they're further away from the nucleus, right, as you go down the group. Across the period, right, the number of shells is remaining the same, whereas the nuclear charge is increasing. So shielding is remaining the same, but the number of protons in the nucleus, or the positive charge in the nucleus, increases, so the outer electrons are actually attracted more strongly and held closer to the nucleus. Okay, you see the same trend for period 2 across period 2, and you see the same trend across period 3.